In this lecture, we're going to introduce a concept called the confidence interval, and we'll go through how to actually calculate a confidence interval. And the confidence interval is a type of inferential statistic in which we use a range of sample data to determine the range of population means that are not significantly different from the sample mean. And to explain this, we first introduced a concept that we've already addressed sometime here called a point estimate. And a point estimate refers to just that, a single point, a single numerical value obtained from sample data. In other words, the average calculated from a sample is one example of a point estimate. An interval estimate is referring to a range of sample data that we think with a degree of confidence within which the population mean resides. Now, note that this is not the same thing as a standard deviation about the mean. The standard deviation, yes, it is an interval, but it's not an interval estimate of the population. The standard deviation calculated from a sample is directly that represents the variability in the sample and not necessarily that of the population. But what we want to do here is we want to use the sample data, the average, as well as the standard deviation to make a statement about the population mean and where we think the actual mean of that resides. And that is within what we call the confidence interval. And so with the confidence interval, we set up specific boundaries. Those are called confidence limits that we think contains the population mean. Remember, we only have a sample of data. We don't have access to the entire population, so we're making a guess in terms of whether the sample data is reflective of that population. And the way we do that is we calculate what's summarized as CI, or the confidence interval, and that's equal to the sample mean. So X bar is the sample mean, and we add and subtract, so plus minus, the product of a particular Z value that corresponds to what's called a confidence level and the standard error of the mean. So once again, this is our sample mean. This is our Z-score, and we need a particular percent of interest for that Z-score. And the standard error of the mean referring to the equation in which the standard deviation of the sample is divided by the square root of the sample size. And that quotient is the standard error of the mean, and it carries the exact same units as the standard deviation. So in developing a confidence interval, what we need to decide upon is that level of confidence. And typically we go with 95% or 99% level of confidence, not both. But usually, most of the time, we settle on 95%. And so in using the 95% confidence interval, we're using limits, an interval that captures 95% of the area under the normal distribution. And that occurs when the Z value, or the standard deviation value, of plus minus 1.96. So almost two standard deviations, as you can see illustrated on the graph here below, negative 1.96 Z plus 1.96 Z, and collectively under the normal curve, that captures 95% of the population. And in our confidence interval, we would be 95% confident that based upon the sample data, the population average would reside within that range. So to do this, we need to use the sample mean, and we need the standard error of the mean. And using these fictitious data here we have, in this sample study, we have a sample size of 42 people, and it was already calculated that the standard error of the mean is 1.36. Once again here, what we're looking for are the 95% confidence limits at plus minus 1.96, corresponding to an area of 95%. And so when we calculate the confidence interval, we're 95% confident that the population mean will reside within this interval. To state differently, that leaves us with a 5% chance that the population mean is actually not in the interval that we calculate. So using these fictitious data here, what I'm doing is I'm calculating the confidence interval around an average of 40. So if we have a sample average of 40 and we want to calculate the confidence interval around the sample data within which we think the population average resides, then we take the average of the observed average of 40 in our sample, and we plus minus the product of 1.96. Remember, we settle on 1.96 because we determined that we want 95% of the area under the curve. And we multiply that by the standard error of the mean. And this was already calculated here at 1.36. So we first carry out the multiplication on the right-hand side, which leaves us with 40 plus minus 2.76. And then we add and subtract 2.76 to 40. So that leaves us a range of 37.33 and 42.67. And so what we can state with 95% confidence is that the population average for these data will reside somewhere in this range, remembering that our sample average, which we directly observed, is 40 in this particular example. Now, in reality, when we deal with research studies, sample sizes are considered relatively small. And so when we calculate a confidence interval, we have to consider the fact that small sample sizes do have an effect on making the normal curve more flat or more platykurtic. And as a general rule of thumb, the number 30 for a sample size is where where considerable flattening occurs, although it does happen at values larger than 30. And so instead of using the Z distribution, we would use something called a T distribution. The T distribution is symmetrical like the normal distribution or the Z distribution, except that the T distribution is flatter, as you can see in the red and the blue images here that are also symmetrical. And the reason why they're flatter is that when we have relatively small sample sizes relative to very large population, the variability decreases with larger sample sizes. So as the sample size gets bigger, the distribution, the frequency distribution, becomes more narrow. And T-distribution curves are more platykurtic. As a result, we don't have just one T-distribution, we have many T-distributions because the T-distribution depends on sample size, and that's what we see in this illustration on the bottom of the slide. So the red here illustrates the T-distribution for a small sample size. And in this sample size here, we see this is a degree of freedom of 3. And so I'm going to add 1 to this, and that gives us a sample size of 4, because with a degree of freedom, we always take the sample size and we subtract 1. And you can see the red is quite flat. If the sample size were to double from 3 to 6, or rather the degrees of freedom doubles from 3 to 6, what we see here is that the curve, the blue curve, still symmetrical, becomes more narrow until we get to theoretically an infinitely large sample size, which would equate our population, where we now see the T distribution cannot be distinguished from the normal distribution. And so the 95% limits for these 3 different curves are illustrated with these numerical values. Recall the normal distribution has 95% confidence limits at plus minus 1.96. But at much smaller sample sizes, so with a degree of freedom of 6, so the sample size here would be 7, a degree of freedom of 3, so the sample size would be 4, we see that the 95% confidence limits get wider and wider and wider. And so to determine what the actual t-value is in calculating a confidence interval, we use what's called a t-table. And in this particular t-table, we have 3 levels of confidence along the top here. So we have 90%, 95%, and 99%, but we typically use the 95% level. The first column is the degree of freedom, and that's determined by the sample size subtract 1. So you can see here that we have a number of sample sizes that are actually quite small. They do get larger, but we'll talk about the largest one here shortly. So as we move from the top of the table towards the bottom, you can see that the sample size gets larger and larger and larger until it gets to an infinitely large sample size, which in theory is the size of the population. And we typically use the 95%. So in this particular table, it shows 90 and 99%. And if we take a look at the t-value, in the previous few slides, we had a z-value. But because we're dealing with small sample sizes, we now have a t-value. So if you can see here, at a sample size of 6, this is a degree of freedom, so 6 minus 1 is 5, so we add 1 to the degree of freedom to get our sample size. We have a confidence limit of plus minus 2.571. But as we move down the table, sample size gets larger and larger. The confidence limit gets narrower and narrower. And so these values, the 95% confidence limit, starts to decrease until we get to the infinitely large sample size, which is the size of the population. And now the t-value takes on the exact same value as the z-value on the normal distribution, which represents a population of 1.96. And these are all plus minuses. And so this illustrates the manner in which we calculate a confidence interval with relatively small sample sizes. And this ends this video on confidence intervals.